Hello everyone, welcome to our EXA4MIND webinar. The webinar is about the benefit of EXA4MIND technology for Aquaview. My name is José Terán and I represent the company Terraview in EXA4MIND construction. Today we're going to talk about the system integration of EXA4MIND technologies to the Terraview product Aquaview, and we're going to check the benchmark results of this integration to see how beneficial EXA4MIND is in practice. Let's start with some context to understand Aquaview, what it does, what it is, and how it helps to solve the soil erosion problem. Nowadays, the soil health and the soil erosion are a big concerns. There are some practices that contributes to this problem of the soil erosion. For example, the over-irrigation practice. That one of the effects of this is that it compacts the soil, it limits the airflow, and limits the root growth of the plants. On the other hand, not enough irrigation can dry the surface, weakens the soil, and makes it easier to erode. Also, the over-irrigation could cause a business problem to farmers, since water not managed efficiently translates into money that is wasted. That's why we developed the Aquaview product, which is a sensorless soil moisture prediction tool. This approach eliminates the needs for expensive and physically installed probes in the field. Instead of relying on hardware that requires maintenance and limited sampling points, Aquaview uses existing satellite data to calculate and predict the soil moisture level of some parcels. The Aquaview's goal is simple: keep the soil at the right moisture level to protect its structure and avoid unnecessary spending. How? Simply by minimizing the hardware cost and providing a high resolution and daily data, which allows for efficient and precise water applications that directly solve the problem of waste and soil degradation that we just discussed. Here we have a more elaborated diagram of the Aquaview product. We can see its architecture, and we can divide it into some parts to easily understand it. The key part is the soil moisture content prediction in this section. And before it, we have a full pipeline where the satellite images are downloaded. These satellite images are later on analyzed for the prediction. And this is one key concept, one key part that we are going to be discussing in this webinar. Okay, so everything starts with a user request for an analysis of a parcel of an area of interest for a specific time range. The request goes through an Apache Airflow orchestrator that sends the request to Microsoft API Planetary to identify the URLs of the images that will be downloading. The images URLs are authenticated for security, and after that they are downloaded from an Azure storage. Once the download finishes, the images go through a process of cloud and shadow removal to remove the pixels that are considered clouds or shadows or snow. Once that is done, a special clipping takes place, which is basically removing all the pixels of the image that are not that do not overlap the area of interest. And at the end, we are going to see just a small portion of the parcel, of the image that overlaps the parcel. In parallel, we also query data from the Open Topography Elevation API, which provide us data about the surface, the elevation, and the temperature of that area. Once all that data is triggered and prepared and processed, the soil moisture content takes place. Once that is done, the results are stored in an SQL database in a local file storage where the system executes the pipeline, and some notifications are sent to the users. Now, to understand the Aquaview integration with EXA4MIND, we need to discuss a few concepts that are key. One of them is the geotiff. A geotiff is just a regular image that includes location information. It contains the coordinates, map projection, and system reference of the image. This allows the image to be located at some point on Earth. This is an example of a geotiff in a coast of Portugal. This is just an example. And this is an illustration of the geotiff that contains pixels and geo coordinates. In the pipeline I just showed before, in the current architecture of the Aquaview product, the satellite images that are downloaded are these ones, geotiff. The key concept of this integration is this, the cloud optimized geotiff. A cloud optimized geotiff is still a regular geotiff, but it is styled and it includes built-in low resolution copies, like you can see right here, so that the user system that that downloads and requests this information, it only downloads the necessary data for the area of interest instead of the full image. So if the parcel or the area of interest that you are processing only overlaps these pixels right here, the pipeline could download only these pixels, not these ones. This is a comparison with the geotiff, since in the geotiff you usually download the full image. They are for sure optimized to work over the internet in comparison to regular geotiff. A normal geotiff is built for local storage, since each image could be in the size of 100 megabytes, give or take, depending on the image coverage. But on the other hand, cloud optimized geotiff are just few kilobytes of data. We can see an example on QGIS of a full geotiff right here, the one I showed before, in the coast of Portugal. And if we check the properties, we can see that it is usually, the size is 76 megabytes approximately, which is a lot. And in comparison with cloud optimized geotiff, it's just this a small portion right here. If in the properties we can see that the cloud optimized geotiff is just 3 kilobytes, which is much less data. In case that the pipeline is processing only few parcels in this section, the current architecture of Aquaview will download the full geotiff file, but at the end, in the clipping, it will only get this small portion. It will be beneficial if we can initially only download this small portion. The pipeline will be much more optimized and scalable. And this is where EXA4MIND comes into play and provides a lot of benefits. Let's go to the presentation and we will get there. Another key concept is a stack. A stack is a JSON-based standard object that describes geospatial assets. It contains metadata, search, catalog collections. And this is an example of a stack response of EXA4MIND that contains scenes, cloud coverage, and its scenes IDs. And this is the stack response of Microsoft Planetary Computer. Cloud masking. As I mentioned before, the cloud masking is an important process that removes the pixels that have clouds, snow, or shadow, because they need to be ignored during the prediction, since they could affect the tool. Now let's talk about the EXA4MIND platform architecture, the usage and advantages for Aquaview. In this slide, we can see some key improvements, such as flexible combined usage of data backends, Postgres and iRODS, the usage of EXA4MIND general stream data workflow control approach for Aquaview pipeline, Apache Airflow. Also, we have a build-up of a satellite data cache system and a cache management and data download workflow in Airflow. And lastly, we have the setup of a spatial temporal asset catalog stack. All this is to make the satellite data flow for Aquaview much more efficient using the cloud optimized geotiff. Now, in this view of the EXA4MIND architecture, as you can find it on docs.exa4mind.eu, the idea is to have a set of modules for common tasks in extreme data processing. For each deployment of this EXA4MIND platform, we can flexibly choose and combine the modules we need in a specific application, such as our Aquaview. So I will point out now what is the relevant usage for our application case. At the heart of the EXA4MIND architecture, we have the Advanced Query and Indexes System, AQIS. This module has components for implementing the stream data workflows. It provides us with support for the caching system based on iRODS, which is a modern data management system for distribute and tier storage. Also, we use its engine, Apache Airflow, for satellite data cache management and for the Aquaview in general. The dataset connectivity, this one. Let's see if I can, yeah. The dataset connectivity and fair support module provides dataset indexing and cataloging components. In our case, we use a stack as we need a system for geospatial data. All the components shown here are or will be available as source codes or installation receipts with the open platform repositories. If you're interested in this status, check out docs.exa4mind.eu. The EXA4MIND benefits could be summarized into these three, basically. If we take the cloud optimized geotiff concept and we somehow integrate it into the satellite imagery pipeline, we can see these benefits, such as the acceleration of the processing time through optimized data retrieval. We can see a reduction of the storage requirements and an enhanced scalability for concurrent multi-parcel processing. So it means that we can download much more images that covers a bigger area of interest. This diagram describes the integration of EXA4MIND and Aquaview, and I will explain how it works briefly. Everything starts from the download of satellite images from the US Geological Survey database. These images go through an ingestion service that afterwards go through a pre-processing tools where the cloud masking happens in this part. This ensures that the images they are already clean. This is just a way to say they don't contain contaminated pixels by snow or shadow or clouds. Once that happen, the images are stored in an iRODS storage, and other data such as cloud coverage, a capture date, they are stored in another database, a metadata database. In the Aquaview side, we start by making a request to the Stark server, and the Stark server knows the area of interest that we want, and it fetch all the data that is needed. Once that data is retrieved back, the Aquaview product starts the content prediction, the soil moisture prediction with some workers. This is another diagram of the integration. and the same pipeline that we saw before, but with the EXA4MIND technology plugged in. We can see in the part of the satellite imagery that we had before, that now is much more reduced with the EXA4MIND technology. We can see now that we have an EXA4MIND stack, the iRODS storage, and a streaming download process. Once this pipeline will work with the cloud optimized GeoTIFF. The rest, it remains the same. And this is the key concept of the integration. Everything else remains the same: the user request, the patch orchestrator, and the only thing that is changing is the EXA4MIND technology plugin in this part. This technology is called iRODS. Now, to validate this integration, we develop a benchmark. And we are going to discuss the methodology of this benchmark. We perform the benchmark in 3 different configurations, 3 different scenarios, 28 and 4 CPUs, simulating a high-end server cloud instance for 20 CPUs, a mid-range workstation, 8 CPUs, and for the 4 CPUs workers, it will simulate a laptop or personal computer. So we can get better insights how this technology works. So we will be comparing the current architecture of Aquaview downloading images, and we are going to compare the iRODS technology downloading images for the same soil moisture prediction pipeline. In this image right here, we can visualize the benchmark process. It starts with a pre-fetch phase where we fetch the geometries that will be downloaded. Shortly, I will share an image of these parcels. We make a query to the prod stack, to the Planetary Microsoft API, and then we do a query to the iRODS stack. We take the statistics of these responses into the benchmark analysis. Afterwards, a prod phase starts. We start downloading the images using workers. The workers are just threads that could run in parallel. The amount of threads that run in parallel are given by the amount of CPUs that are being used in that scenario. So for example, for this 20 CPU workers, there will be 20 workers in parallel downloading satellite images. For this process, we start a clock timer, and once that all the images from the stack are downloaded, all the images that were identified in the stack are downloaded here, we stop the clock and we measure all the stats. The same will happen afterwards with the iRODS phase. The same amount of workers downloading the same amount of satellite images. Right here, we can see all the parcels. We selected 42 real agricultural parcels from the Terraview API database, ranging from 1 to 41 hectares in size. And this distribution represents the realistic field sizes across different agricultural regions. For each parcel, the Landsat imagery was queried for a 60-day period from October 4th to December 4th of 2025, around 270 scenes per branch. The current implementation of Aquaview and the iRODS approaches, they both process identical parcels with the same geographic stance, which makes sure that it ensures that there is a fair comparison in the benchmark. These are the key concepts that we are measuring: total processing time, uh, that is the wall clock elapsed time for the complete processing phase, the total data transfer, which is the accumulation volume of data retrieved from remote storage across all successfully processed scenes in bytes, mean data downloaded per parcel, the average data transfer volume per agricultural parcel. We also measure the mean time per parcel, the average total processing time per agricultural parcel, the standard deviation time per parcel, and the waiting time per hectare. And finally, the mean stack query time per parcel. Okay, now we can see the benchmark results for the different configurations that we did, 28 and 4 CPUs. But before going into the results, I would like to show how the benchmark works from the code perspective. Okay, once we are in the code, we'll be opening this batch file, which basically does everything. This file copies all the benchmark necessary code to a remote host specified in this variable. That remote host needs to be allowed to use the iRODS technology. Once we copy that files to that remote host, we execute the benchmark, we do some analysis of the report, and the results are back to our machine, all using this batch file. As you can see, we have a list of the scenarios to run and a list of the parcel IDs to run. And for the sake of this demonstration, we are going to limit it to the 20 CPU scenario, and just 2 parcels. Otherwise, it will take a lot of time and to run. But the results with a full suite of configurations are already computed right here in this folder. And these are the results that I will be showing in the presentation later on. The ones that are going to be generated now are just a demonstration. So to start with, we just need to execute the run remote benchmark file. It might take less than 1 minute and a few seconds. You'll see some logs showing everything, how it is going through. And yeah, once that everything is completed, you will have the results right here, like this folder with the report and the parcels. Okay, I will be removing this one. This is just a demonstration, and we can analyze the final results that we get right here. Okay, for each scenario, we have the parcels that were downloaded, and inside each parcel, we have the TIFF. We have the iRODS TIFF, the ones that were downloaded using the iRODS branch. They are cloud optimized GeoTIFF indeed, and the prod TIFF that were GeoTIFF, not cloud optimized GeoTIFF, and afterwards in the pipeline they were clipped. And yeah, we get the GeoTIFF for each parcel. We have PNG with some visualization of the statistics that we are going to see in the presentation shortly. And also we have a report CSV file with all the results. Now, to analyze this CSV file, it will be very interesting to see by parcel ID. We can do categorize by parcel ID. And yeah, so let's analyze this parcel that ends in FB5. We can see the area is the same, the time per hectare, and the branch. The branch is prot, the current architecture, and the EXA4MIND iRODS. And status true means that it was downloaded properly. And let's freeze everything right here. Okay. Okay, so we have more information about which scene was downloaded. Each row, it is a scene that was downloaded. So this parcel is the same right here, but each row is a scene. And we can see the scene ID, the scene date, and the cloud cover. So the cloud cover for iRODS is 0 because in the pre-processing tool, it's already cleaned up before it's in the pipeline. Instead of the Microsoft Planetary software, it's the cloud masking happens afterwards. Yeah, we can see an URL of the image, and now we can see a more important statistics right here in these columns. We can see the static query time was, okay, yes, of course, the same for this parcel. And yeah, it's way faster for iRODS than prod. We can see the bytes downloaded column, and this is a key statistics to see. As you can see, the bytes downloaded, it's a huge number, while for the iRODS, it's a very slow number. But when we are seeing this column output in megabytes, we can see that both outputs are almost the same. Almost the same. It means that there is a waste of data in the prod, since not all the pixels are used. In comparison with iRODS, it downloads everything that is needed. And with these numbers, it's easy to see where the optimization is located. We can see the lapse time to download, the download time, the clipping. There is no clipping for iRODS, but yes, for the prod architecture, bandwidth megabytes per second. You can see a huge improvement, and some metadata of the files. Okay, back to the presentation. With the 20 CPUs, the traditional prod system took 4 minutes, while iRODS took 40 seconds, and there is an improvement of almost 7 times on speed. And this is processing the same amounts of parcels and the same amounts of satellite images. You may wonder why is the difference, and in this row we can see it. The amount of data, it's huge. The difference is huge. Yeah, while prod downloads over 20 gigabytes of data, iRODS only downloads 0.2 megabytes of data. And iRODS outperforms the production architecture in all the scenarios, possible scenarios. And this is a demonstration of the benefits of this amazing technology. For the ACPUs, the traditional prod system took 6 minutes to finish. iRODS completed the same work in just 37 seconds, 10 times faster. The reason is the same. Prod downloads 77 megabytes per field, while iRODS transfer less than 1 kilobyte. Even with fewer CPUs, iRODS deliver major time savings by moving far less data. And for the scenario of 4 CPUs, the system needed nearly 10 minutes. The production system. iRODS just finished in only 44 seconds, which is 13 times faster. Even with limited hardware, iRODS stays efficient because it downloads minimal data. In fact, the fewer CPUs available, the bigger the advantage. This makes iRODS ideal for cost-effective cloud deployments or systems with hardware constraints. Yeah, in summary, we tested prod and iRODS across different CPU configurations, 28 and 4 CPUs, processing 42 agricultural fields, and iRODS consistently outperform the prod in every scenario. And the key is simple. It downloads less data and it gets faster results. Thanks a lot for your attention. My name is Jose Teran, and bye bye.